Earlier I mentioned that velocity was one of the most important features or characteristics of moving water in terms of its ability to move material around the landscape. Now what I want to do is to concentrate on this diagram here, and I'll walk you through exactly how to read this diagram so you can understand the different pieces of it. First of all, on the x-axis, what we're looking at are changes in the size of material. So the smallest size material is clay, and moving from there up to silt, sand, gravel, and pebbles. As the size of the material gets bigger, you would expect it also gets heavier. So pebbles are heavier than gravel, and gravel is heavier than silt. So just keep in mind that as you move from left to right on this graph, you're increasing the size of the particles that can be moved by water. On the y-axis, what we're looking at is a change in velocity. So the faster the water moves, it's at the higher or the top of the graph, and the slow-moving water is going to be at the bottom part of the graph. Both scales in this graph are logarithmic, meaning that they don't increase by equal amounts at every interval. So in size, we go from very, very small particle sizes in clay that are less than 0.01 millimeters in size, up to pebbles, which can be fairly large, as many as 100 millimeters or 10 centimeters in diameter. For velocity, this graph goes from 0, so standing or still water, all the way up to 1,000 centimeters per second. Okay, on this graph, what I want you to pay attention to next are the different lines that separate the shaded areas on the graph. We're going to start with the line that represents the minimum velocity that's necessary for erosion. So I'm highlighting that in purple here. So it's this line right here. What this line indicates is that any time the velocity is greater than that line, it's capable of moving a particle size, or it's capable of picking up and transporting particle size that is equivalent at that particular velocity. So if we were to look at, for instance, a 1 millimeter piece of gravel, so here, and we were to look where that intersects the line, what it indicates is that we need about 30 centimeters per second velocity in order to pick up that piece of gravel. So remember, a lot of what we're talking about here is the ability to pick things up, to transport it, and then to drop it off. So clay, or the easiest things to move, are actually sand. So sand to small gravel has the lowest velocity necessary for it to be entrained or picked up. Pebbles, however, have a very high velocity that's necessary to pick them up, and that's because they're heavy. So they're heavier things, they're bigger, they require a higher velocity in order for that to be moved across down the stream channel. What might be a little bit surprising, though, is that it also takes a fairly large or fairly high velocity in order to move material that's down here in the clay and silt area. The reason for that is that clay in particular is so small, it has a very high ability to adhere to itself. So it takes a higher velocity water to actually break that material up and to get it to start moving. You might think about this from when you were a kid and you were cleaning off the driveway of dirt. It's always easier to move the dirt that's sort of crusted onto the driveway off with a hose if the hose is kinked and the velocity of the water is much higher. So the higher the velocity, the easier it is to move that material. So that's what this line, this purple line, is indicating here. And so in general, what it shows is that it's difficult to entrain clay and small silt. It gets easier as you get through sand, and then as the particles get heavier and heavier, it gets harder and harder to get them to move or to be entrained within the flow of the water. Now, the other line on this graph that I want to pay some attention to, I'm going to highlight in orange, and that's this line right here. This is the line where if the velocity dips below that line, anything that has been entrained into the flow of water will start to fall out. So what you're seeing here is that this one doesn't have the differences in terms of clay versus silt, but it's almost entirely based on the weight of the material. So first of all, you'll notice that down here in the area where there's clay, what we find is that the clay can stay entrained and be moved by the water. Once it's entrained, it's going to be there for a fairly long time. And it doesn't take much velocity at all to keep it moving. But the bigger the material gets, you have to actually keep the water moving really fast, otherwise it drops out of suspension. And so, for instance, pebbles, big pebbles at 10 centimeters, it takes about 200 centimeters per second velocity to get that moving. But if you drop down to about 150, it's going to fall out of suspension. So it's going to drop in that particular area. So what this graph allows us to do is to recognize that there are three different zones in terms of the velocity of the water that have different characteristics regarding the ability of that water to either pick things up, move it, or drop it off. So this dark gray zone in the bottom right is the zone of sedimentation. So that's where things are going to fall out of suspension in the water, and they're going to end up on the ground or the bottom or the bed of the channel. The light gray area at the top, up in here, this area is where material is being eroded. So it's being picked up and brought into the water column so that it can be moved. Everything in the center of the graph, in the white area, is in the zone of sediment transportation, which means that the sediment is being moved by the river. So this graph is really important for understanding the different ways that water actually moves material around the landscape. So the things to remember about this is that there's three different processes that are in play here. Erosion, picking up the material and training it. Transportation, moving it within the water column and moving it downstream. And then finally, sedimentation, which is the dropping out of the material from the water column onto the bed or the floor of the environment in which it's being deposited. So those are the three things that I want you to be able to understand about this. The next thing that we're going to do is we're going to look at some examples, or one particular example of how all of this comes into play and how it's impacted by the activities of humans along the coastal plain of South Carolina. Okay, so now let's take the information that we have from the figure before and put it into operation in a real-life situation. So remember, it's all about picking stuff up, transporting it along the river, and then dropping it off. And it's all related to velocity. So the faster the water moves, the more material can be picked up and moved, and the slower the water moves, it tends to drop more material off. So the example that we're going to look at is one from the coastal plain of South Carolina. And here, in this map, what I want you to pay attention to is the distribution of water features here. So you can see that this is the coast of South Carolina, right along here. And there are a couple of features that are important for you to at least know where they are. So first of all is the city of Charleston. Charleston is located right in here. So Charleston, South Carolina is a large port. It's a commercially important port, and it's a historically important location. The river that flows into Charleston Harbor is the Cooper River, and the Cooper River moves across the Piedmont and then down through the coastal plain and eventually into Charleston Harbor. Above the Charleston Harbor are two reservoirs. There's Lake Marion and Lake Moultrie. These two lakes, or these two reservoirs, are man-made reservoirs. They were created in the early 1900s by damming the Cooper River. and also damming another river that's really important here, which is the Santee. The Santee River is this river that goes from Lake Marion, right about here, and flows out to the Santee Delta. The Santee is a really important river because it's one of the naturally largest rivers on the eastern seaboard. Historically, though, there are some things about this that are important. So if we think back to the way that the United States was first settled, remember that it was a mercantile economy where things were produced in the colonies and then sent back to Britain. So everything is going on ships back across the Atlantic Ocean over to Britain. That means that there had to be good harbors. And so Charleston Harbor was a really important commercial harbor, both through the colonial times and up through modern history. So, for instance, all the BMW roadsters are built in South Carolina, and they all are transported all over the world through Charleston Harbor. The reason that this is important with regard to the rivers is that if you remember the history of the United States, initially all of the colonization was right along the coast, but eventually people started moving further and further inland. So as people moved inland away from the coast, it was important that they have major rivers that were able to transport materials down to the coast and into the harbor, the major trading harbors. So the largest river on the coastal plain of South Carolina was the Santee, but the Santee didn't have a good port. So it wasn't very easy. It was easy to get into the interior, but it was hard to get it out to Britain. The opposite was true of the Cooper. The Cooper River was not a very big river, but it had a great port. And so there was this sort of mismatch of cities and ports along with major rivers as the United States grew and the economics of the colonies began to change. So that's the historical context of what goes on in this particular area. The other piece of this is to recognize that there is a delta that is right here, right at the mouth of the Santee River. This delta is important as an area for waterfowl, and it has a lot of biodiversity in that area. But it is also subject to all the conditions that are present at all deltas. So deltas form when fast-moving water in a river empties out into a body of still water. And in this case, the still water that it's emptying into is the Atlantic Ocean. So the fast-moving water of the Santee moves out, hits the Atlantic Ocean, and all of a sudden its velocity drops. So what we remember from the figure that we looked at before, as the velocity drops, so does its ability to hold material or to keep material entrained in the flow of water, and all that material starts to sediment out. And so that's how the deltas are formed, and it's how the Santee Delta was formed here. So now, what's actually important about this from modern times? Let's take a look at another situation or another set of historical characteristics that were going on here. In 1941, there was legislation that was passed that allowed for the diversion of the Santee River. So this was the damming of the Santee River, which ended up creating the reservoirs on the South Carolina on the Piedmont of South Carolina. So in 1941, the Santee River was dammed. Lake Marion and Lake Moultrie were created, The result of this was that all of the water that used to flow down the Santee, remember from the previous picture where the Santee River was, it was now held back. It was held behind a dam, and this changed where the water ended up moving. And so more of the water ended up going out through the Cooper River than the Santee River. So what this did is it completely changed the flow characteristics of the two rivers. This was entirely a man-made activity, And it was done for a variety of reasons. Mostly it was done for hydropower generation. The dams that are put into place along the Santee River were generating hydroelectric power. And this all was going along fine, but what this did is it completely changed the hydrology of the system. So remember, we used to have the Santee being one of the largest rivers on the eastern seaboard, and all of the material that was in that river would empty into the Santee Delta. Well, now all the material that is being carried along by that water as it moves down the coastal plain is instead moving into the Cooper River and is being emptied into Charleston Harbor. Well, this causes a little bit of a problem. The Cooper River is emptying all this sediment into Charleston Harbor, but Charleston Harbor needs to be a deep water port. Charleston Harbor is the location of, at the time, Charleston Air Force or Charleston Naval Base. So there were large naval ships that came into Charleston Harbor. There were also a lot of commerce that came into Charleston Harbor. And so the harbor itself had to be kept very, very deep to allow for these large ships to come into the harbor. It also was a submarine base. And so submarines would come in and actually go up the Cooper River. And they were able to do that because the river was now deeper than it used to be, and that was an ability to get to the submarine base. So the problem was that this cost a lot of money. It cost a lot of money to dredge the harbor every year, and they had to dredge it every year to take all of that sediment that used to be going to the Santee Delta, but was now emptying into Charleston Harbor. And they had to move all that sediment out. So they would come in with dredges, they'd scoop all of the sediment out of the harbor and move it away. It cost a lot of money to do that. So in 1968, the Army Corps of Engineers was authorized to re-divert the flow of the Cooper River back into the Santee. So the problem is that people got used to the flows in the river being what they were, and this ended up being a little bit problematic. But in 1968, they decided that they authorized the building of a tail race canal that would move things from the bottom of the lower reservoir back into the Santee River, and so more water would be going down the Santee. The result of this would be less sediment in Charleston Harbor, more sediment out onto the Santee Delta. So the other thing that was happening, Charleston Harbor was filling in with all of this sediment because it was now coming down the Cooper River, but the Santee Delta was receding because not as much material was being deposited onto the Santee Delta. So they were losing wildlife habitat at the Santee Delta and gaining a lot of sediment in a place where they didn't want it. So they said, well, we diverted the water, let's redivert it. And in true fashion, what they did is they went ahead and decided that they would put hydroelectric power generating facilities on the tail race canal so that they could generate even more electricity along the canal as it brought water back into the Santee. Now, the tail race canal was completed in 1985. So by 1985, the rediversion canal, or the tail race canal, was done, and now they had the ability to change the entire flow system back to a little bit more of what it was to begin with. But the problems that they ran into here were that now there were economic activities that depended on more water going through the Cooper, and so they had to balance what was capable of happening in those two situations. So now they had economic reasons to keep the water up high in the Cooper, and at the same time they had economic reasons to keep the water low in the Cooper. So they never actually completely rediverted all of the water back into the Santee. Never happened, and that had some effects on the forest that was along the Santee River. Okay, so now if we look at the map of what was happening here again, remember that there were two dams that were put into place. One of them was here along Lake Marion. One of them was here along Lake Moultrie. And what they did is they created the two reservoirs. Then they authorized and completed the building of the Tailrace Canal, which allowed for water to move from Lake Moultrie back over here into the Santee. So, and they put hydroelectric power generating facilities along that Tailrace Canal. Now, if they had brought it back to what was normal, then they would have expected to see increasing sedimentation occurring here along the Santee Delta, decreasing sedimentation here where in the Cooper River, along the Cooper River and in Charleston Harbor, and things would have been back to sort of pre-colonial ways or pre-colonial conditions, along with the fact that they're generating hydroelectric power in the Piedmont. One of the things that did happen, though, was that the vegetation changed considerably along the Santee River. So there's a bottomland forest that's located right about here, and many of the species that were dependent upon the flooding of the river ended up disappearing in that area because of the changes in the flood system. They originally had planned to increase the flow in the Santee back to what it was to pre-colonial times, but it never actually got that way, and so you still saw real changes in the biodiversity of the lowland forests along the Santee. So the reason that this example is interesting and important is that it draws together a lot of historical characteristics of the eastern seaboard, and it shows that when people go out and do things to the landscape, there are often unintended consequences. All of these things could have been foreseen and may have been foreseen, but they thought they'd be able to deal with them. The increased sedimentation in Charleston Harbor had to have been recognized, and so did the reduction of the size of the delta of the Santee. But over time, they decided that the risk reward was less, and so they built the Tailrace Canal to move things back. So it's an interesting example of how the interplay between people and their environment changes over time based on both economic and cultural values for different types of systems.